In this lesson, we're going to be deriving the formula for the surface area of a sphere. So last lesson, you looked at volume. This lesson, we're looking at surface area. So does anyone have an idea what the surface area of a hemisphere would look like? So a hemisphere, of course, is half of a sphere. So just think about what that might look like. Is a soccer ball really a sphere? That's a great question. And it's really not. It's called a truncated icosahedron. So we have learned our Platonic solids by now, and we know an icosahedron is a polyhedron with 20 faces that are equilateral triangles. And we know that's not what a soccer ball is. The soccer ball is that icosahedron with cuts made on it. That's what truncated means. And so here's a picture of it doesn't look like a soccer ball, but that's really what a soccer ball is. It's made up of hexagons and pentagons. Here's the net of a soccer ball. So a soccer ball is not truly spherical. Is a baseball. A baseball is truly spherical, but the material that we use to make baseballs is kind of stretchy, and that's what allows that to be put together. So in our surface area of a sphere, we've been looking at this dialogue between Dee and some other people, Penny and Miss Poshlet and all that. And so she is realizing that she needs to know about surface area of spheres. And so she's thinking about what the net of a hemisphere would look like. And a hemisphere, of course, being half of a sphere, would have a base that is a circle. It has that flat part that's a circle. But what about the lateral surface area she's thinking about? We know it's half the surface of a sphere, but what does the surface of a sphere look like as a net? And so she peels some apples because those are kind of spherical, and oranges because they're kind of spherical, but doesn't really have any progress toward her goal. And then she remembers that her friend Penny is back from her vacation to Walt Disney World. And so she's going to go see her to see if she can help her visualize what a sphere is. So Penny shows her about a place that she saw at Disney World called the Epcot Spaceship Earth is what this is. And it's at the Epcot park. And it looks a lot like a sphere, but it's really not a sphere. It's really a geosphere that has 11,324 triangles on its surface. And so Dee's really wondering how in the world this is going to help her with the net of a sphere. But Penny says, what if we imagine the surface of the sphere being made up of a bunch of triangles? If we could find the sum of the areas of all those triangles, we could at least estimate the surface area of a sphere. So Dee has a thought, and she is going to see if the volume of a sphere will help her find the surface area, since we learned about volume yesterday. So we're going to be looking at how can we use triangles to approximate the curved surface of a sphere. Have anyone ever seen a geodesic cone? It looks very much like a hemisphere, but it's a half of a sphere, but it's made up of triangular faces, so you can see here. So I just thought it'd be cool for you to kind of see what those are. So we're going to use what we learned about volumes yesterday of pyramids and spheres and help us derive the formula for the surface area of a sphere today. So imagine this sphere is made up of thousands of skinny little pyramids. We can see one of them right here. So you can see them repeating that over and over and over. And what if we just kept repeating that till it completely filled in the entire sphere? So let's look at the volume of the pyramid. We know it's 1/3 the area of the base times the height. We use capital B for area of the base. But in this case, the height of the pyramid is the radius of the sphere. It goes from the center of the sphere to a point on it. So it's its radius. So we could say the volume of one pyramid is 1/3 the area of the base times the radius of the sphere. So the volume of the sphere would be the sum of all of the volumes of those little pyramids. So you can see we would have just lots of them. We could repeat this addition over and over and over and over again. So we would have 1/3 base area. We use these subscripts to show that they're different ones that we're talking about, times the radius of the sphere. And so we would literally have that over and over again for all of those little tiny pyramids. So we can factor out the common factors of 1/3 and r that is in every single one of the terms. So we bring out the 1/3, we bring out the r, and that leaves the sum of all the base areas inside. So we know if we add up all the base areas of all the pyramids, that makes up the surface area of our sphere. And so this is where we are so far with our thought process. We took the volume of all those little pyramids, factored out the parts they had in common, the 1/3 r, and all the sum of their bases add up to make the surface area of the sphere. So question 1 in your notes, it says use what you learned about the volume of each solid to derive a formula for the surface area of a sphere. So right now we have the volume is equal to 1/3 the base area. Volume equals 1/3 the radius times all the base areas added together, which is our surface area of the sphere. So that's what we've gotten so far. So we know that the volume from yesterday is 4/3 pi r cubed. So we can replace V in our formula with that formula from yesterday. And I'll make this big for you guys, sorry. So this is what we got from the animation. The volume is 1/3 the radius times the surface area, because remember it was 1/3 base area 1 times r plus 1/3 base area 2 times r plus, and we kept doing that. So we factored out the 1/3 and the r that they all had in common, and that left the sum of all the base areas of all of those pyramids. And those base areas make up the surface of our sphere. So that is the surface area. So I'm replacing the volume with the formula that we learned in our last lesson, 4/3 pi r cubed. And so now I can solve for surface area and get the formula for surface area. So the first thing I'm going to do is I'm going to multiply both sides of this equation by 3 so that I'm no longer dealing with a fraction on either side. So now I have 4 pi r cubed equals 1r, which is just r, times the surface area. So I'm really close to getting surface area solved for. I just need to get rid of that r that's being multiplied by it. So we know to get rid of it, we need to divide both sides by r. So these r's cancel, leaving me with surface area. So I can simplify this because I have r to the third over r to the first. So if you'll remember from Algebra 1, that meant you had r times r in the numerator and 1r in the denominator, and one of those pairs cancels, leaving you with r squared. Or in other words, you can subtract those exponents. 3 minus 1 is 2. So the surface area of a sphere is using the formula 4 pi r squared. Now pi r squared should look familiar. Pi r squared is the area formula for one circle. So the surface area of a sphere is like having 4 circles. So one activity we used to do in geometry is we would find the circumference of a orange. So we would measure its circumference, and we would use that to find the radius of the orange, and we would draw circles with that radius of that orange, and we would just draw those circles, and then we would peel the orange, and we would see how many of those circles we could fill up with the peeling of the orange, which was its surface area, and it would completely fill up 4 of those circles. And so that's how we learned that the surface area of a sphere is the area of 4 circles, 4 pi r squared. So it says, Okay, it says, wow, that was impressive. She came up with the formula, surface area equals 4 pi r squared. So if we could draw the net of a sphere, its area would be the same as 4 circles, just like you described. So surface area equals 4 pi r squared is in fact a correct formula for the surface area of a sphere. So what will the surface area of the chocolate hemisphere be? So a hemisphere is half of a sphere, but that does not mean the surface area is half of the surface area of a sphere. Because think about this. Surface exposed this part, the lateral area, is half of a sphere, but you have a circular base that you have to include as well. So looking at question 2 in your notes, I don't want you to think about just finding surface area, which is 4 pi r squared, and then dividing that by 2 to find the hemisphere. That would not be the correct surface area. So you have to think about what's exposed on the surface. Yes, you have this dome that's half of the sphere. That is half of that 4 pi r squared. But you also have that flat circular base on the bottom, which is another circle. So if we look at simplifying this, we have 2 pi r squared plus another pi r squared, which is equal to 3 pi r squared. So that's how you find the surface area of a hemisphere. Surface area of a sphere is 4 pi r squared. Surface area of the hemisphere is 3 pi r squared, not half of the sphere. So hopefully you understand it's because of that flat circular bottom. So you can see here, if we were finding that with our chocolate hemisphere, we were given the radius of that to be 2. So to find the area, the surface area of the whole sphere, we would use the radius of 2 in the formula 4 pi r squared. So we have 4 times pi times 2 squared, which is 4 times 4 is 16 pi. That's exactly the surface area. That would be centimeters squared. But we can approximate it to the nearest tenth as 50.3 centimeters squared. The surface area of the hemisphere, remember, is 3 pi r squared, not 2. 3 pi r squared. So we're just replacing the r again with 2. 2 squared is 4. 4 times 3 is 12. So it's exactly 12 pi centimeters squared, but as rounded to the nearest tenth, that would be 33.7 centimeters squared. So it says, do you think it's possible to unfold a sphere into a net? And no, it's not really possible because a sphere has surfaces that are curved, and so you can't really flatten it out very well. If you took the leather off of a baseball, it does have kind of an interesting look to it. You have this kind of circle joined to this other circle, and then you have the same thing happening on this end. So that's a really crude drawing, but you kind of can see the 4 circles that you get the area of for the surface area, but you can't really flatten out a sphere. All right, good luck on your homework.